Okay, in this morning's class, we're going to talk about multicast technologies for the service provider CCI lab exam. Then some other topics today. We'll take a little bit of a look at some layer 2 VPN solutions. We'll talk about some troubleshooting techniques that you want to use in the lab exam. Some more information about where to go from here preparation-wise. So let's get started with multicast for today. Now, up to this point, everybody should be pretty comfortable with configuring basic intra-AS multicast, which is going to be enabling PIM in sparse mode or dense mode or sparse dense mode, and configuring basic RP assignments within an individual autonomous system for running multicast. Now, some of the things that we need to think about before we get into configuring multicast is, first off, is our IP version 4 unicast routing domain working correctly? Okay, because multicast is going to require unicast routing in order to perform its RPF check, and we'll see there will be some exceptions that we can get around this with static multicast routing and multicast BGP we'll take a look at today. But the majority of the time what you're going to see is that we're going to be running IGP within the domain, and protocol independent multicast is going to use that IGP in order to support the reverse path forwarding check that we're going to need in multicast. And now, technically, within the service provider lab exam, you could think of multicast as not necessarily a core technology, because nothing else really in the exam is going to depend on it. Things like building your IGP, building your MPLS transit network, that's going to be real key, because without that stuff, you can't build any VPNs or have any reachability on top of it. But multicast on its own, even if you were to get somewhere in the range of 10 to 12 points in multicast, you could theoretically just blow it off completely and then still pass the lab exam. Okay, so it's not going to be as core of a technology as stuff like MPLS and MPLS VPNs, but you definitely want to be familiar with this topic for the lab exam. Okay, now, when we are building the multicast network, first thing we want to think about is to build the individual intra-AS configurations before we get into any more complex configurations like multicast BGP or MSDP or multicast support for MPLS VPNs. Okay, so what we're going to do here, we're going to talk about the different PIM modes. We'll take a look at doing some basic configurations of intra-AS, and then we'll look at how to add some of the advanced service provider technologies on top of it. Okay, now, first option we have here for configuring PIM is going to be in dense mode. Pretty straightforward configuration. The only consideration really that we need to worry about is the RPF failure inside the IGP domain. And again, what the RPF failure is when the router receives a multicast packet, it's going to look at what is the source IP address of this packet. And then it's going to correlate that with the IP routing table and say what is the outgoing interface for this source. Okay, so it's receiving the multicast packet in, and it's looking at what interface do I use in order to reach this source. If the incoming interface for the multicast packet and the outgoing interface for the unicast route are the same, then the reverse path forwarding check is successful. Okay, if the multicast transit path is different than the unicast path, then we can see a failure of RPF check, and the router is going to drop packets when that occurs. Okay, so we'll see some situations when that's going to occur, and then what the different methods we have in order to solve it. Okay, another design problem we could run into with dense mode PIM configurations is on multi-point and non-broadcast links. We could possibly run into an issue where we have basically a split horizon type behavior with multicast, where let's say, for example, we have a frame relay hub and spoke network or an ATM hub and spoke network, where the hub receives a multicast packet in from the spoke. It's not going to be able to forward it out to the other spoke, assuming that they're using the same logical interface, whether it's the main interface or it's a multi-point sub-interface. And now, in service provider designs, this is typically not that big of an issue because, like I mentioned earlier, service providers are typically going to use point-to-point links between their devices. You're not going to find a lot of logical multi-point configurations in the network. Okay, but if you're running dense mode, that is going to be an issue. And basically the only way that we could get around it would be to either run sparse mode to get this PIM NBMA mode behavior, or to tunnel it over something like GRE, for example. Okay, so configuration-wise, PIM dense mode is going to be pretty straightforward. We just enable multicast routing globally and then enable PIM on the interface. Okay, then we'll go through the different verifications here as we are when we look at this on the command line. Okay, now sparse mode is going to be a little bit more involved than dense mode, and the difference in the logic between the two is that dense mode is going to assume that everyone wants all multicast traffic unless they specifically say, I do not want the traffic. A sparse mode is going to be the opposite. The routers are going to assume that no one wants the traffic unless the endpoints specifically request it. Okay, now this request, it's going to be tied together with the central point of the network that's called the rendezvous point. Okay, the rendezvous point is the meeting point for the multicast clients and the multicast servers. And when we look at this on the command line and look through some debugs, we'll see exactly how the multicast tree is merged at the rendezvous point. Okay, now, since we're dealing with this rendezvous point in the sparse mode network, we need to figure out how we are going to assign it. Okay, we can either do static statements just to say router 1 is the rendezvous point, or we can do automatic assignments either through Cisco's AutoRP or the open standard bootstrap router, which is BSR. Okay, we'll also look at a different variation of this today, which is called Anycast RP, which technically, it's not a way to assign rendezvous points. We could do Anycast RP assignments statically or through AutoRP or BSR, but it is a consideration that you want to take into account related to sparse mode multicast. And now, just like dense mode, sparse mode multicast is going to be subject to the RPF checks in multicast. And we could possibly have that NBMA mode problem where we have traffic coming in one interface and we need to send it back out an interface. A sparse mode does have a method to get around that, which is basically the IPPIM NBMA mode command on the interface. Okay, so our sparse mode configuration is going to be a little bit more involved than dense. We're going to enable multicast routing. We'll enable sparse mode on the interface, and then we're going to have to figure out how we're going to do our RP assignment. Okay, now, we can do the RP assignment a couple different ways again. We can do it statically, we can do it with AutoRP, or we can do it with Bootstrap Router. Okay, now, based on how we are doing the assignment, there are going to be some differences in running PIM in sparse mode, which says that all groups must have a rendezvous point, versus sparse dense mode, where we're saying groups that have a rendezvous point will be sparse, and groups that do not have a rendezvous point would be dense. Okay, there's a question here, do we also need to perform the RPF check for the rendezvous point? And yes, we do. Okay, so when we take a look at this on the command line, we'll look at some debugs to see what is going to happen if the RPF check fails on either the multicast stream or the traffic coming from the rendezvous point. Okay, so this is the main topology that we're going to be looking at for today, dealing with multicast routing. So we're going to look at it first with two different autonomous systems. Then we're going to combine this autonomous system into one to look at Anycast RP configuration and multicast support for MPLS VPNs. Okay, so the first thing that we're going to do is configure basic sparse mode inside AS456, and we're going to use AutoRP with router 2 as the rendezvous point. And in AS456, we're going to configure router 4 as the rendezvous point, and we're going to do this automatically through BSR. Okay, router 7 and router 8, we're going to use them to simulate both multicast clients and multicast servers. Okay, the multicast server configuration is just going to be by sending traffic to a multicast destination. Okay, the client functionality is going to be based on the IP IGMP join group command that Cisco routers support on the interface. Okay, so that's just going to be for testing purposes to generate a PIM, to generate an IGMP join message so that the PIM neighbors can propagate the PIM joins up to the rendezvous points. Okay, so let's go ahead and take a look at the command line And we'll start to build this topology, and then we'll look at how the basic verification and troubleshooting is going to work for sparse mode. Okay, so the first thing that we want to do, here is test basic layer 2 reachability within these individual autonomous systems, and then make sure we have basic IGP reachability. Okay, so if we look at from router 8, we should have connectivity here over to router 6, which we do. From 6, we should be able to get down to router 5. From 5, we should be able to get down to router 4. Okay, now there is a link that is between 5 and 1 that we're going to be looking at, but we'll take that out of the picture for right now. Okay, router 4 should have connectivity down to router 2. Okay, 2 has connectivity to 1. 1 should have connectivity to 3. And then 3 should have connectivity over to router 7. Okay, so now that we're sure that we have basic layer 2 reachability, let's go ahead and configure IGP. And between routers 1, 2, and 3, we'll run OSPF. And then between routers 4, 5, and 6, we'll run a separate OSPF domain. Okay, so these BGP autonomous systems, the separate BGP autonomous systems, they are not going to be exchanging IGP information with each other. Okay, they're just going to be exchanging BGP information. Okay, so on router 3, we'll go ahead and run OSPF. And we'll advertise, we'll just say everything in the 150 network is going to be in area 0. Area 0. Okay, so on all of these routers here, we'll basically just go ahead and drop this configuration off. Okay, now between 2 and 4, so under the process here of router 2 for OSPF, I'm going to say passive interface fast Ethernet 1/0 because we do not want to exchange IGP information between these BGP autonomous systems. Okay, now we have some non-broadcast links here, so we'll say on the ATM, we'll say we're going to run OSPF as a point-to-point network type. Okay, same thing on router 2's ATM, IP OSPF network point-to-point. And then the same on the frame relay connection between router 4 and router 5. We'll say IP OSPF network point-to-point. And likewise on router 5. Point-to-point. Now again, in the service provider lab exam, we're not really as concerned about layer 2 technologies as we are in the routing and switching lab exam. So stuff like this, like changing the OSPF network types and getting basic connectivity, you should assume that you're allowed to do whatever is necessary to build basic reachability, unless there are specific requirements in the exam telling you not to do that. Okay, so in this case, not going to waste time trying to define unicast neighbors and worry about the designated router election on these OSPF segments. We're just going to run it as the most logical network type, which is going to be point-to-point between these two neighbors. Okay, so we see 6 has a neighbor with router 5. So if we look at the routing table now, show IP route OSPF. Okay, nothing yet. Let's go ahead and check our adjacencies. Show IP-OSPF neighbors. Okay, so we are adjacent with router 5 there. Okay, so there we go. So router 6, we should have reachability all the way down to router 4, which is 4.4. And if we look on router 3, show IP route OSPF, ping 151.2.2. Okay, so we have basic IGP reachability within the network here. Okay, there's a question here. I think, yeah, there's an error in this diagram. Let me bring it back up here. This here on the bottom left, this should say router 2 is going to be the rendezvous point for AS123, not 456. Okay, that should say for AS123. Okay, so we have basic IGP reachability within the domains. So now we can configure PIM to run on top of our IGP. We're going to assign router 2 as the rendezvous point for AS123 via AutoRP. And we're going to assign router 4 as the rendezvous point in AS456 via Bootstrap router. And now if we take a look back at, let's see, PIM, sparse mode, considerations. For AutoRP, there's a couple of design issues that we need to take into account with AutoRP. That there's kind of a recursive logic that goes along with AutoRP. In order for AutoRP information to be propagated throughout the multicast network, there's two groups that we need to join. Okay, these are going to be the 224.0.1.39 group and the 224.0.1.40. Okay, we need to join these groups in order to get information from the mapping agent and to get information from the candidate rendezvous points. Now, the problem that we run into is that sparse mode PIM says I cannot join a group unless I have a rendezvous point. But AutoRP says you need to join these groups in order to learn about the rendezvous point. So we end up in kind of a recursive logic where it's saying you need to join the group to learn about the RP, but you need to learn about the RP to join the group. And now the ways we can get around this is by running PIM in sparse dense mode. So we're going to say that this group is going to be dense, and this group as well. So we do not need a rendezvous point in order to join these groups. Okay, there's also a feature called AutoRP Listener, which says that specifically for these two groups we're going to be dense and everything else will be sparse, or we could do a default rendezvous point assignment. Okay, so where statically we could say that, for example, router 2 is the RP for these two groups, and then everything else could be dynamically assigned through AutoRP. Okay, so in our case, we'll go ahead and just enable the AutoRP Listener feature, which is going to allow us to treat these two groups as dense on the interface. Okay, so it's not going to be like sparse dense mode where we can have other groups in dense operation. It's going to allow us just to have these two AutoRP groups as running in dense mode. Okay, so let's go ahead and enable multicast routing on routers 1, 2, and 3. We'll run PIM on the interfaces between them, and then we're going to distribute the rendezvous point information on router 2. Okay, and there's another question here. Who is going to be the mapping agent? We're going to assume that router 2 is going to be the mapping agent as well. Okay. Likewise, in BSR, we're going to have router 4 as the RP candidate, and it's going to be the BSR candidate. Okay, so in this case, they are the rendezvous points, and they are propagating their own rendezvous point advertisements. Okay, so on router 3 first, we'll go ahead and enable multicast routing. Save my configs here. We'll say IP multicast routing. We're going to run AutoRP Listener, so IP PIM AutoRP listener. And now, depending on what version you're running, this command may or may not show up in the context-sensitive help. So you may not be able to tab through this command. You may have to type the whole thing out. Okay, but even though it's not in the help, the majority of the newer versions support it. So if you type the thing all the way out, then you should be able to get it to the parser to take it. Okay, so we're running multicast routing. We're running AutoRP listener for PIM, and we're going to say on serial 2/1. This is 1.2 actually. IP PIM is in sparse mode. Okay, so same thing on router 1, we'll say IP multicast routing. IP PIM AutoRP listener. On the serial connection over to router 3, IP PIM sparse mode. And then the ATM link over to router 2. Okay, so at this point, we have basic PIM configured on the interface. So next step we're going to do is verify that our adjacencies have formed. So we're going to look at the show IP PIM neighbor output. Okay, so we should see here shortly, assuming that, let's take a look at the interface here. Assuming that we have multicast allowed on the interface, which we should, show IP PIM neighbor. Okay, so we see now we're adjacent with router 1 over the ATM link. If we go over to router 1, we should see neighbors, show IP PIM neighbor. We see neighbors with router 3 and with router 2. Okay, now on router 2, we're going to configure to distribute its rendezvous point information. Okay, this advertisement, when we source it, we're going to source it from the loopback interface of router 2. It could basically be any route or any interface that devices in this domain have reachability to. Okay, so we could source it from our ATM link, we could source it from our loopback, we could source it from our Ethernet. As long as everyone in the intra-AS multicast setup, it has a route back to this link. Okay, now whatever interface that you are announcing the advertisement from, that interface should also be running PIM. So in this case, we're going to go to our loopback interface, we'll say IP PIM sparse mode. Okay, so in global configuration, we'll configure router 2 now to propagate this information. We'll say IP PIM send RP announce. We're going to source this announcement from our loopback. And the announcements will have a time to live of 255. Okay, we don't care what the TTL is. Okay, we can also change the interval that we're advertising out, or we could say we want to announce ourselves only for these specific multicast groups. In this case, we're going to announce ourselves for everything. Okay, now we're going to send the mapping agent messages. Okay, the send RP announce, that is for the candidate RP messages. Now we're going to actually tell everyone that router 2 is the rendezvous point. Okay, so these operations, they could be on two separate devices, they could be on the same device. As long as everyone has reachability to the RP, and assuming that there is not an RPF failure on the way from the rendezvous point to the mapping agent, and there is not a reverse path forwarding failure from the mapping agent to all of the other multicast routers. Okay, so with AutoRP, you're performing the RPF check on both the mapping agent and on the mapping agent and the candidate RPs. Okay, so we'll say IP PIM send RP discovery. We're going to source this discovery message from our loopback, and we'll say it has a time to live of 255. Okay, so once we're announcing these, next thing we want to do is go to the other routers in the PIM domain and check what their group to RP mappings are. Okay, we should see that we are automatically learning about router 2 through AutoRP advertisements. Okay, so if we look at router 1, we're going to say show IP PIM RP mappings. So we can see now from the show IP PIM RP mapping output on router 1, we learned about router 2 as the rendezvous point. This was elected via AutoRP. And we can see the group range that router 2 was elected for is the entire multicast range, 224.0.0.0/4. Okay, so this range is going to be 224.0.0.0 through 239, 255, 255, 255. Okay, so that's the entire range. If we go down to router 3, we should also see this as well. Show IP PIM RP mappings. Okay, we can see that router 2 is the rendezvous point. Okay, so we saw first off, we had basic PIM adjacencies between the neighbors, and we can see now our rendezvous point information is being propagated properly. Okay, the next thing that we want to test is, can sources properly register with the rendezvous point, and can destinations properly propagate join messages up the PIM tree to the rendezvous point. Okay, the rendezvous point is going to be the meeting place for the source and the destination. When the source starts sending into the network, the designated router on the segment is going to send a unicast register message up to the rendezvous point. It's telling the rendezvous point, I now know about a server that is sending into the network. If you have clients that want to get this group address, then you need to merge those two trees. Okay, likewise with the PIM join message for the client. Okay, whenever an IGMP join message is received on an interface, the router is going to propagate that message up to the rendezvous point saying, I have a client that is trying to get traffic for this group. You have a server that's already sending it to it, you need to merge those two trees together. Okay, so what we're going to do on router 3 here, on the client-facing interface, which is Ethernet 00, this is going over to router 7, we'll enable sparse mode PIM, IP PIM sparse mode, and we're going to advertise this link into OSPF. Okay, so under the OSPF process, we'll just say network 10.1.37.3 is in area 0. Okay, but we don't have any routers on that segment we want to be adjacent with, so I'll say passive interface Ethernet 00. Okay, so we want to make sure that everyone inside our multicast network has a route back to the host segment. Okay, now on router 7, who's the client, we'll just go ahead and configure a static route going out to router 3. Okay, and we can see now on router 7, we do have reachability into our unicast domain, which is up to router 2. Okay, so let's take a look back at the slides here. Okay, so the first thing we did with sparse mode, we configured it on the interfaces and we verified our adjacency. So we looked at the show IP PIN neighbors. We saw that router 1 was adjacent with 3 and 2. Okay, so that's our first step for verification. Okay, now we want to make sure that the rendezvous point is properly assigned. So we're going to go everywhere and say show IP PIM RP mappings. Okay, once the RP is assigned correctly, we can verify that can we send join messages up to the rendezvous point, and can we register our sources with the rendezvous point. Okay, so we're going to simulate a client by using the IP IGMP join group command on the interface. Okay, we're using this only for testing purposes to make sure that a PIM join message can be propagated up towards the rendezvous point. Okay, so what we're going to do on the routers in the path, on routers 1, 2, and 3, we're going to debug IP PIM. We're going to debug IP PIM. Then on router 7, we'll create a join message, and we should see that propagate up through the multicast network up to router 2. Okay, so first thing we're going to do on router 3, we'll say debug IP PIM. Okay, no logging console, logging buffered. Okay, same thing on router 1. Don't log to the console, we'll log to the buffer. debug IP-PIM. Okay, so now everybody is debugging their PIM information to the logging buffers. Okay, so on router 7 here, we'll go ahead and on the interface facing into the provider network, which is going to be Fast Ethernet 3, we'll say IP IGMP join group 224.7.7.7. Okay, so some arbitrary group that we're sending a join message into the network. Okay, so we send this join message out to the all router multicast address. And if we look at router 3 now, if we show log, we can see that we received a join message for 224.7.7.7. Okay, it says star comma 224.777. So it means that it is not a source specific join. Router 7 is just saying, I want to get any traffic that is going towards the group 224.777. And now we can see it says we're inserting star comma 224.777 in a join message for our neighbor 150.1.13.1. If we look at the rendezvous point, if we say show IP-PIM RP mappings, we can see that router 2 is the rendezvous point. Okay, when we receive this message, the next thing we do is say show IP route 150.1.2.2. We can see the route towards the rendezvous point is upstream towards router 1. Since router 1 is our PIM neighbor, we go ahead and forward the join message up the multicast tree in order to get closer to router 2. If we look at router 1, we should see the message received from router 3 and then propagate it up towards router 2. We can see we received a join message from router 3. It was destined to us. Router 3 told us it has a client that is interested in joining 224.777. So we're adding the serial interface to the multicast tree. So we're saying in the outgoing interface list, when we look at the multicast routing table, we should see serial 2/1 in the outgoing interface list for this group, 224.777. And now we're forwarding the message upstream towards router 2, who is the rendezvous point. If we look at router 2, we should see the same thing. Show log. We received on the ATM interface from router 1, we received a join message that was about the group 224.777. Okay, so if we look at the multicast routing table now, show IPM route, what we're saying is that if traffic comes in to from any source, we don't care what the source is, but if the destination is 224.7.7.7, we're going to forward this out the ATM link. Okay, once it goes out the ATM to router 1, if we show IPM route, we'll say specifically for 224.777, it would be coming in the ATM, which is the upstream interface towards the RP. We're going to forward it out serial 2/1 out towards router 3. If router 3 were to receive this packet, if we show IPM route 224.777, it would be coming in the serial from router 1. It would be going out Ethernet 0/0 towards the client. And now it's very important to do this basic verification in the network, because if this is not working up to this point, then all the other advanced features that are going to sit on top of multicast aren't going to work. We need to make sure that we can build the basic shared tree up to the rendezvous point. Okay, so this is the first step. We can see that clients, when they join the group, when clients are joining a group, their join messages are being propagated properly up to the rendezvous point. Okay, now we're going to send traffic into the network from router 7 and make sure that the source properly registers with the rendezvous point. Okay, so router 3 should receive this message and send it as a unicast packet up to router 2 saying, I learned about this source that is now sending into the network. Okay, so let's clear our log information here. And on router 7, we'll go ahead and do an extended ping. We'll say we're going to ping 224.77.77.77. We'll send a bunch of packets. Extended commands, yes. We're going to send it out interface, fast Ethernet 0/3. The source address is going to be our interface address, 10.137.7. Okay, now when you are generating multicast traffic for testing, you want to make sure that you do an extended ping to say specifically what is the interface I'm sending it out and what is the source address going to be. If you just do a ping to the destination, it's going to send it out all interfaces, even if PIM is not enabled on those interfaces. Okay, but for a true test to make sure what happened if a client was actually there or a real server was there, you need to make sure it's going out the interface that is running PIM and is coming from the correct source address. Okay, so we're sending that traffic out the interface now. If we look at router 3 and say show log, what we should see here is that we received a packet from 10.1.37.7. They are sending traffic to 224.77.77.77. Okay, we are sending a register message towards the rendezvous point, 150.1.2.2. Okay, this is a unicast packet that we're sending up to router 2. We're taking the multicast packet, which is coming from 10.1.37.7, going to 224.777. We encapsulate it inside a unicast PIM packet and send it as a register message up to the rendezvous point. Okay, so now router 3 is telling router 2 there is a source that is sending into the network. Okay, router 2 is saying back, I received your register message. Stop sending me those unicast packets. I understand now that there is a source sending into the network. Okay, if we go up to router 2 and say show log, we see that we received a register message from router 3. It says the source was 10.1.37.7. They were sending to 224.77.77.77. Okay, so we're adding this into the multicast routing table. Now we're telling router 3, stop sending me those unicast messages. I understand that there is a source sending into the network. Okay, so router 3 generates the register. The rendezvous point is replying back with the register stop message. Okay, if we look in the multicast routing table now, show IP mroute for 224.77.77.77. We see that we know there is a source 10.1.37.7. Okay, if we take a look at router 1, show IP mroute, we're not going to see on router 1 the entry for 224.77.77.77 because there's no clients in the transit path going through router 1, and the messages router 3 is sending to router 2 are unicast. Okay, so let's take a look back at the diagram here. Okay, so the first thing that happens here is that router 7 is sending traffic into the network. Okay, router 3 is the PIM designated router for the segment. Okay, if there were multiple routers on the link, then only one of them would be receiving the packet and sending the register message. Okay, so router 3 receives the traffic from router 7, it encapsulates it inside unicast, and it sends it up to router 2 as a register message. Okay, router 2 says, I know that there is this source now. I'm replying back with a register stop. Now, router 1, who is in the unicast transit path, did not look at this packet because it is not multicast between router 3 and router 2. It's a unicast register message router 3 sends. Router 2 replies back with a unicast register stop. Okay, so until there is a destination in the network, router 1 is not going to know that there is a server in the path. Only the rendezvous point is keeping track of the state of the entire multicast network. So everything is going to flow up to the rendezvous point. Once the rendezvous point knows about clients, then it is going to merge the server's tree with the client's tree. And if we went to router 2 and we joined that multicast group on the loopback, for example, then we should see the multicast transit path be built end to end. Okay, so if we go up to router 2, and let's go to its loopback, and we'll say IP IGMP join 224.77.77.77. And we look at router 7 now, we see we're getting ICMP echo replies back from router 2. This means that router 2 is receiving ICMP messages going to this address, and just like any other normal ICMP echo request, it's replying with a unicast echo reply. Okay, so if we look at the multicast domain, if we look at router 1, for example, and we say show IP mroute 224.77.77.77, we can see that we know about the source 10.1.37.7. It's coming in serial 2/1. It's going out the ATM interface up towards router 2. Okay, if we look at router 2, we should see it coming in the ATM interface. Show IP mroute 224.77. Okay, we see what's coming in the ATM interface. We're forwarding it out the loopback. Okay, so at this point, we can tell inside AS123 we have our basic multicast functionality working. We have clients that can send their join messages up to the rendezvous point, and we have servers that are sending, and those register messages are properly getting up to the rendezvous point. Okay, again, without testing this basic functionality, anything else that goes on top of this, if we're running Anycast or MSDP or multicast BGP, we don't want to get ahead of ourselves in the configuration and verification, because once something goes wrong in the multicast network, a lot of the times it's really hard to troubleshoot. Because multicast inherently it's really slow to converge, and sometimes you'll run into an issue where you're troubleshooting something that doesn't need to be troubleshot. And once you get to that point, if you have a lot of complex configuration, then it's really hard to figure out where to start. So as you're building the network, you really need to test it on a bit-by-bit basis like this. Okay, so there's a question. So router 2's loopback is acting as a client for that group, correct? Okay, so router 7 is acting as a server that's sending out a multicast stream. Router 2 is acting as a client that wants to receive that traffic. Okay, so this IP IGMP join group command, we're using it only for testing that the multicast tree is built properly. Okay, that's the only practical application for this command. So in the lab exam, in practice labs, you see this used a lot because there's no real host that you have to test multicast reachability. Okay, but just keep in mind, this command doesn't enable PIM or enable IGMP on the interface. It's used just to simulate a client sending a join message into the network. Okay, so now that we have our AutoRP network built in AS123, let's go over to AS456, and we're going to configure router 4 as the rendezvous point via Bootstrap router. Okay, so first thing we're going to do, we're going to say IP multicast routing. And then on the interfaces, we'll say IP PIM sparse mode. Okay, when we're running BSR, we don't need to run PIM in sparse dense mode, and we don't need to use the AutoRP listener command. Okay, the reason why is that the BSR messages are not multicast to their own address. Okay, they are sent on a hop-by-hop basis inside of the PIM message. Okay, the PIM message is automatically propagated hop-by-hop inside your regular PIM adjacency messages. Okay, so right now, router 4 and router 5 are running PIM on the interface. We can see now they're adjacent. Okay, when router 4 goes to do its BSR advertisement, inside these PIM messages, it's telling router 5, I am a rendezvous point via Bootstrap router. Okay, so typically this design using BSR makes a little bit more sense than AutoRP, but if you have older versions of iOS in the network, you may need to support an AutoRP design, but either BSR or just doing static RP assignments would be, design-wise, would be a better idea than using AutoRP. Okay, so we'll run sparse mode on that interface as well. Then on router 6, IP multicast routing. Then PIM over to router 5, IP PIM sparse mode. Okay, additionally, we'll run PIM on the client-facing interface, okay, which is this is the link connecting to router 8. And under the OSPF process, we'll go ahead and advertise this in network 10.1.68.6. But we don't have any routers on that segment, so we'll say passive interface gigabit 01. Okay, there's a question here. Is the tree built from the source to the rendezvous point? Okay, the tree from the source to the rendezvous point is a shared tree, and the tree from the client to the RP is a shortest path tree. When they use the term shared tree versus shortest path tree, a shared tree means that the multicast traffic is transiting through the rendezvous point. Okay, anytime the traffic comes from the server, goes up to the rendezvous point, and then from the rendezvous point goes down to the client, that is the shared tree. Okay, a shortest path tree would be where it goes directly from the server to the client without transiting through the rendezvous point. Okay, now in this case, there's not going to be any difference between the shortest path tree and the shared tree because there's only one physical path in the network between the neighbors. Okay, but the shortest path tree means it's not going through the rendezvous point. The shared tree means that it is going through the rendezvous point. Okay, technically you could have a shortest path tree that it is going through the rendezvous point, which is the case that we have now, because there is no difference in the physical transit path. Okay, so let's go ahead and check our PIM adjacencies. We'll say show IP PIM neighbors. Okay, we see we're adjacent with 5. If we look at 5, show IP PIM neighbors. We're adjacent with 4 and 5, or 4 and 6. And on 4, show IP PIM neighbors. We see we're adjacent with router 5. Okay, so at this point on router 4, we should be able to propagate our information through BSR and then go to router 5 and 6 and look at the show IP PIM RP mapping output. Okay, now just like in AutoRP, we're going to send this announcement from our loopback. So on router 4's loopback, we're going to say IP PIM sparse mode. Okay, some versions of iOS, you need to do this. Some versions you don't. Sometimes the iOS will give you an error message if you don't do it, if you don't put PIM on the loopback. But as a general rule, whatever interface is participating in multicast, okay, whether it's for a source advertisement or it's a transit interface, you need to enable PIM on that interface. Okay, so client-facing interfaces, you'd run PIM. The transit links between the routers, you're going to run PIM. And then any interface you're sourcing advertisements from. Okay, so globally here on router 4, we're going to say IP PIM RP candidate. We're going to source our RP candidate messages from our loopback. And we are going to announce ourselves as a bootstrap router. We'll source those messages from our loopback. And that's all we need to do. So IP PIM RP candidate from the loopback and IP PIM BSR candidate from the loopback. Okay, there's other options that we can add onto this. How often do we want to send our updates? Which specific groups do we want to service? If there are multiple candidate RPs in the network, what happens if if we're trying to service the same group? We can do like a priority to do a tiebreaker. In this case, we're just doing basic configuration. We're assigning router 4 as the BSR and the rendezvous point. Okay, so if we look at router 4 locally, if we say show IP PIM RP mappings, we can see this system is a candidate RP, and this system is a bootstrap router. Okay, we can see it says version 2. Okay, anytime you see the term PIM version 2, it's referring to BSR. Okay, the difference between PIM version 1 and PIM version 2 was that BSR was standardized in PIM version 2. Okay, so if we had a question that said configure PIM version 2 in the network, I would assume that they are referring to BSR. Okay, so if we say show IP-PIM RP mappings, we can see router 4 is the rendezvous point. We learned about router 4 via Bootstrap. And we should see the same thing on router 6. Show IP PIM RP mappings. Router 4 is the rendezvous point. We knew about them through Bootstrap Router. Okay, so at this point, we know we have our basic PIM adjacencies, and our RP information is propagated throughout the network. Okay, now we want to send a client join message to make sure that is propagated up to the rendezvous point, which will be our star comma G entry. Then we're going to send traffic into the network to a multicast group, and we should see our S comma G entry being built. Okay, so from router 8 here, we'll say IP routing, and we're just going to do a static route out into the network. So IP route to 10.168.6, and we should have reachability up to router 4, which we do. Okay, so if we go ahead and on our interface, that's Ethernet 6, we'll say IP IGMP join 224.8.8.8. Okay, now when we look at the multicast routing table of routers 4, 5, and 6, we should see a star comma 224.8.8.8 entry that is pointing down towards router 8. So router 4 is going to be the source of the tree because it is the rendezvous point, and we should see this star comma G entry going downstream towards router 8. Okay, so if we look at router 4, show IP mroute 224.8.8.8, we see the outgoing interface is serial 0/0. If we look at router 5, we should see the incoming interface is serial 00, and the outgoing interface is Ethernet 01. And then lastly, on router 6, if we show IP mroute 224.8.8.8, we should see the incoming interface as gigabit 00 and the outgoing interface as gigabit 01. Okay, so again, what this is telling us here is that when an IGMP join message was received from a client, we properly sent this as a PIM join message upstream towards the rendezvous point, and the shared tree was built from the rendezvous point towards the client. Okay, we have our star comma G entry saying that whoever sends, if anybody ends up sending to 224.8.8.8, I know where to send that in the network because I have clients that are interested. Okay, now if we go ahead and source traffic into the network, we'll go ahead and ping 224.88.88.88. Extended commands, yes. We're going to send this out, fast Ethernet 06. We're going to source it from 10.168.8, which is the IP address on that interface. Okay, so what we should see now, if we look at router 6, we should see an S comma G entry. We should see, when we say show IPM route, we should see 10.1.68.8, comma, 224.88.88.88. So if we show IPM route 224.88.88.88, we see that S comma G entry. Okay, we see it's coming in the gigabit 01 interface, but the outgoing interface is null. Okay, the outgoing interface is null because there are no clients that are interested in joining that group. Now if we look on router 5, show IPM route 224.88.88.88, we don't have an entry for that. But if we look at the rendezvous point, we should see this because router 6 should have sent us this information as a unicast register message. And we can see that we do know about the source. Okay, so at this point, router 5, who is in the transit path, doesn't know about the source because the multicast tree has not been built. Okay, we have an S, G entry at the designated router, which is router 6, and at the rendezvous point, who is router 4. Okay, until someone actually joins the group, until we have a client in the group, the rendezvous point is not going to merge the server's tree and the client's tree. Okay, so if we go to the loopback here on router 4, and we say IP HMP join 224.88.88.88, and we go back to router 8, we should see these echo replies, which we do. Okay, now when we look at the transit path on router 5, it's saying that when traffic comes from 10.1.68.8, we're expecting it to come in Ethernet 0.1. If it comes in Ethernet 0.1, we're going to forward it out serial 0/0 up towards the client, which is router 4 in this case. Okay, so any questions so far on the basic PIM sparse mode setup? Okay, so when we're building the multicast core, these are the considerations that we need to go through. We need to make sure, first off, do we have basic PIM adjacencies in the network? Okay, so look at our PIM adjacencies. Then we want to make sure, can clients join the groups, and are those joins propagated up to the rendezvous point? Then when sources come into the network, are those sources properly registered with the rendezvous point? Okay, if we have a problem with the reverse path forwarding, we can see this with the show IP mroute count output, and we can debug IPM packets to see what happens when packets are coming in the interface. Okay, we'll look at an example of reverse path forwarding failure in a little bit, and then we'll use these commands, show IP mroute count and debug IPM packet, to actually see those error messages occurring. Okay, so now that we've built our basic intra-AS multicast, we're going to look at what is going to happen when these autonomous systems are trying to exchange multicast information. So we're going to have a source that is inside AS123, but the destination is going to be inside AS456. Okay, now when we're looking at large-scale multicast design, first off, dense mode multicast is not going to be feasible. Okay, imagine if we were running dense mode everywhere on the internet. We would be flooding every multicast packet everywhere, and all the routers in the transit path would have to maintain state information for every single possible source and every single possible client. Okay, so dense mode is not going to be scalable for the internet. It's only for very small implementations where we have a lot of clients inside a local network. Okay, another consideration for inter-AS multicast is that service providers typically do not want to rely on an external rendezvous point for getting their source information and sending their join information. Okay, so service providers, they typically want to keep their network configuration control inside of their own autonomous system boundaries. Okay, so one of the suggestions design-wise where it was, they said we'll have a central rendezvous point or distributed rendezvous points throughout the network, throughout the internet, and then service providers will subscribe to multicast basically by pointing to that rendezvous point. Okay, but most service providers don't want to do that. They want to keep the rendezvous point control within their network. Okay, so the design problem we run into is that when a source registers with the rendezvous point, and inside another autonomous system, a client registers or sends the join message to that rendezvous point, these different rendezvous points are going to have to communicate what is the source and what is the destination. And the protocol that we're going to use to do this is Multicast Source Distribution Protocol, or MSDP. Okay, now MSDP is a TCP-based protocol. It does not have its own transport like PIM does. So in order to establish MSDP peers, we need to make sure that, first off, we have basic unicast reachability between the neighbors. Okay, now what the logic of the protocol is going to do is that when a register message is received at the rendezvous point, again, remember the register message is the designated router telling the rendezvous point that there is a server sending traffic into the network. So there's a multicast source. Okay, when the rendezvous point receives the register message, it is going to generate a source active or SA message to all of its MSDP peers. Okay, so basically what's going to happen if we look at our design here, router 7 is the multicast server. It's the source sending traffic into the network. On router 3 is going to be receiving this traffic, and it is going to send the unicast register message up to router 2. It sends the unicast register message. Router 2 should acknowledge this by sending the register stop. Okay, that's what we saw already happened. Okay, now router 2 is going to tell its peers, its MSDP peers, which is router 4 in this case, it's going to send a multicast source active message saying that I now know about a source that is sending into the network. So the source active is going to be an S, G entry. It's going to be this specific source is sending to this specific destination. If router 4 has a star, G entry for the group, it is going to merge the S, G tree that is learned through router 2 with its own star, G tree, and then multicast traffic should flow end to end. Okay, but the problem that we're going to run into here without MSDP, if router 2 has a register message received and router 4 has a join message received, there's no way that they're going to be able to communicate with each other that I have a server that's sending and I have a client that wants to receive it. We need to bind those two together. Okay, so router 2 and 4, they are binding the source-based tree and the destination tree together. Okay, so let's go ahead and take about a 10-minute break. We'll start back at about 20 minutes after, and when we get back, we'll go ahead and take a look at this configuration on the command line here. Okay, in this morning's class, we're going to talk about multicast technologies for the service provider, the CCI lab exam. Then some other topics today. We'll take a little bit of a look at some layer 2 VPN solutions. We'll talk about some troubleshooting. Techniques that you want to use in the lab exam, some more information about where to go from here preparation-wise. So let's get started with multicast for today. Okay, so let's go ahead and take a look at this MSDP example on the command line. So the first thing that we're going to do is inside AS123, we are going to build our BGP adjacencies. Okay, so what we'll do here, we'll have router 1 peer with router 2 and with router 3. And we're going to have router 1 be a route reflector for IP version 4 BGP. Okay, we could just do a full mesh of peerings, but based on the way the physical topology is here, there's really no reason to peer between router 2 and router 3. Okay, because any traffic that's actually flowing through the network is going to go physically through router 1. And then likewise, in AS456, we're going to peer between 5 and 6, and we're going to peer between 4 and 5. Okay, so router 5 is going to be a route reflector, router 1 is going to be a route reflector. Okay, then at the network edge between router 2 and router 4, we're also going to peer IP version 4 BGP. Okay, because when the traffic comes in from router 7 and router 4 receives this traffic, it's going to have to do an RPF check on the source. So unless router 4 has a route to the unicast source, it's going to be dropping the traffic. Okay, so we need to make sure first up that our unicast information is propagated throughout the network. Okay, so on router 6 here, let's go ahead and run BGP. So router BGP 456. We're going to peer with router 5. And on router 6, we're going to announce this source, the segment that is attached to router 8. So we'll say network 10.1, 68.0 with a mask of /24. Okay, then on router 5, router BGP 456, we're going to peer with router 6. Router 6 is going to be a route reflector client. And then we're going to peer with router 4. 45.4 is a route reflector client. Okay, then on router 4, we will peer with router 5. And then we have our inter-AS peering, router BGP 456. This is going to be over to router 2. So we'll just peer directly connected. 150.1, 24.2 is going to be in AS 123. And on router 2, we're going to say router 4 is in AS 456. And we're peering with router 1. iBGP is going to be in 123. And router 1 is going to peer with 2. And 2 is a route reflector client. And we're going to peer with 3, 13.3. And then lastly on router 3, we're going to peer with router 1. Oops. AS 123. And we're going to announce that segment into the network. So network 10.1.37.0 with a mask of /24. Okay, now at this point, we don't have any MPLS involved in the service provider networks. So we need to make sure that we have a full mesh of BGP in the transit path to make sure that the traffic is going to be able to move end to end. If we were running MPLS in this case, we wouldn't necessarily need to run BGP on router 1 and router 5. We could have done IP version 4 peerings between router 3 and 2, and then 4 and 6, and MPLS would have been tunneling any of the BGP traffic over router 1 and router 5. And when we get to our multicast support for MPLS VPNs, we'll look at that case. Okay, so let's look at the BGP topology now. We'll say show IP BGP summary. We see we are adjacent with router 1. If we show IP BGP, we can see that it says to get to 10.168.0, use 150.1.24.4. Okay, so router 2 is learning the route from router 4. It is not updating the next hop as it is sent into the network. And now, based on the network statement in OSPF on router 2, we already have this interface covered by an OSPF network statement. Okay, so we don't necessarily need to update the next hop value here. If we did not have a route to the transit link between the neighbors, then we would have to go ahead and do that. Okay, but we should see on router 7, we should have reachability over to router 8, which we do. Okay, so now that we have basic unicast transit, we're going to go ahead and between router 2 and 4, we're going to configure them as MSTP peers. Okay, actually, before we do that, let's go ahead. Let's take off our joining configuration here on router 7. So no HMP join. Do the same thing on router 8, show run interface fast Ethernet 6. No IGMP join. Okay, now we're going to use router 7 as the multicast server, and we're going to use router 8 as the multicast client. Okay, so on router 7, we're going to go ahead and send traffic into the network. So we'll do an extended ping. We're going to ping 224.78.78.78. And we'll give it a high repeat count. Extended commands yes. We're going to send this out fast Ethernet 03, coming from 10.1.37.7. Okay, so at this point, with our intra-AS multicast, we should be able to go to our rendezvous point, which is router 2, and we should see the S-G entry installed for 10.1.37.7, sending to 224.78.78.78. Okay, so router 2 should have received the unicast register message from router 3 and installed that in the multicast routing table. Okay, so if we show IPM route 224.78.78.78, we do see the source comma group entry, the S-G entry. Okay, so we can see that the incoming interface is the ATM, but once we receive the traffic, we're not sending it anywhere. Outgoing interface is null. Okay, we don't have any clients that are interested in this group. Now on router 8, who is going to be our client, on the interface connected to router 6, we're going to join IP IGMP join 224.78.78.78. If we go up to the rendezvous point here, which is router 4, we should see our star comma G entry. Okay, so router 4 is going to say that if I receive a source that's going to 224.78.78.78, I'm going to send it over to router 5. Router 5 is going to forward on to 6. Then 6 is going to forward it lastly out to router 8. So if we say show IPM route 224.78.78.78, we do see that star comma G entry. Okay, it says outgoing interface is the serial. Incoming interface is null because we don't have any sources that are sending to the network. Okay, so if we look back at our diagram here, The problem that we're running into is that router 7 is sending the traffic Okay, we have router 7 sending the traffic into the network. It's going over to router 3. 3 is forwarding it, actually the other way. Okay, router 7 is sending the traffic into router 3. Router 3 is sending it as unicast traffic up to router 2. Okay, router 1 at this point does not know that there is a source in the network. It doesn't know there's a source in the network because there's no end-to-end tree built for it. Okay, now router 8 sent a join message up to 6. 6 forwarded to 5. 5 forwarded this to router 4. So router 2 knows about the source, and router 4 knows about the destination, but at this point they are not communicating with each other to merge the source tree and the destination tree. Okay, so by peering MSDP between these neighbors, router 2 is going to send a source active message to router 4 advertising that 10.1.37.7 is sending towards 224.78.78.78. Okay, so on router 4 and router 2, let's go ahead and we'll say no logging console. We'll log to the buffer. Logging buffered. We're going to debug IP PIM, and we're going to debug IP MSDP here. Do a bunch of these. We'll say routes as well. Okay, debug IP MSDP peer and debug IP MSDP routes. Okay, then we'll do the same thing on router 2. Debug IP PIM, debug IP MSDP peer, and MSDP routes. Okay, and then we'll clear the log. Okay, so we're going to peer between router 2 and router 4. Okay, since they're directly connected, we can assume that they already have TCP transport between the neighbors. So if we ping 151.24.4, we see that we have connectivity. Okay, so we're going to say in global configuration here, I want to configure an MSDP peering with 150.1.24.4. When I source my updates to them, I'll send it from my local interface. Okay, in this particular case, you don't necessarily need to do this because it already is going to be the fast Ethernet based on the outgoing interface to the neighbor. Okay, but if we were peering between the loopbacks, then we would have to do this. Okay, the MSDP peering addresses should match the BGP peering addresses. So in this case, I'm peering towards this address in BGP, coming from the fast Ethernet. It should match that with the MSDP peering. Okay, MSDP has some really complex reverse path forwarding checks that are built into it. And if you read about how the MSDP standard works, the vendor implementations kind of just go around this problem and avoid the RPF checks, because when this starts to scale on the internet, the way the RPF is built, it's too complicated to actually work in real implementation. Okay, so another command that you'll typically see used with MSDP is the IP MSDP default peer option. And that says that whenever I receive a source active message, I'm going to advertise it to this neighbor. Okay, and if I receive any source active messages from this neighbor, I am not going to perform an RPF check on them. Okay, so within our case, the network design is typically not going to be large enough for us to see any big problems with this. But we mentioned on Monday there's the book Interdomain Multicast Routing with Cisco and Juniper Solutions, something similar to that. They have some real good explanations on MSDP and how the RPF is going to work. Okay, but in this case, the BGP peering address and the MSDP address are the same, so we're not going to have any problems with this. Okay, so we'll do the same thing on router 4. We'll say IP MSDP peer. We're peering over to router 2. When we source this update, it'll come from our Ethernet address. Okay, so now we'll say show IP MSTP peers. Okay, it says the connection status is up over to router 2. Now, there's a lot of advanced options that you can apply onto MSTP. We can do lots of filtering. We can say what sources do we want to accept, what sources do we not want to accept, what sources do we want to advertise or not advertise. Same with the rendezvous points. But in this case, we're just doing a very basic setup where we're just configuring the peering, and we're not filtering any type of information that we're advertising between the neighbors. Okay, now if we look at the log here, okay, we see we have the debug information for our candidate RP stuff, along with the join for that group. Okay, now we can see inside our MSTP debug, it says we received a source active message from router 2. Okay, router 2 originated a source active message. It was telling us that router 2 knows about the source 10.1.37.7, sending to the group 224.78.78.78. Okay, now since we have a star comma G entry for this, we want to build the multicast tree up towards router 2. Okay, the problem that we're going to see here, though, if we look at the multicast routing table, let's say show IP mroute, we do not see the S comma G entry for this group. Okay, we saw from the MSDP debug that router 4 did learn about the source. It's 10.1.37.7, comma 224.78.78.78. Okay, it also knows about the destination. It knows that there's a client somewhere out serial 00 that wants to join this group. What router 4 and 2 need to do is merge these trees together with PIM join messages. So in addition to running MSTP between the neighbors, the autonomous systems are going to have to exchange PIM information. Okay, so we need to make sure that on the network edge, we are running PIM with the remote neighbors. So router 2 and router 4 are going to have to run PIM. Now, one of the problems we can run into here is that as soon as we enable PIM on the interfaces, we're going to start leaking our rendezvous point information between different autonomous systems. Because on router 4, we're running Bootstrap router. That is going to be advertised out all interfaces that are running PIM. On router 2, we're running AutoRP. Those informations, the mapping agent messages, are going to go out any interface that is running PIM. So before we enable PIM on the interface, what we would actually want to do is make sure, we need to make sure that these messages are not going to leak out to the other neighbors. Because AS456, they should not be using the rendezvous point that is inside AS123. And likewise, AS123 should not be using the RP that is inside AS456. Okay, so the way we're going to do this, there's two different methods. For AutoRP, we're going to tell router 2 not to advertise that information out the Ethernet interface, the fast Ethernet. Okay, so what we're going to do, we're going to create an access list that says deny the 2 AutoRP groups. Okay, deny those AutoRP groups. Then we're going to allow everything else. We're going to apply this as a boundary configuration to the interface. Okay, so we're saying if traffic is going to any of these destinations, it is not allowed to go out that interface, and it is not allowed to come in that interface. Okay, for BSR, there's a command that's built in specifically to do it. We just say IPPIM BSR border. It means that we will not accept or send BSR advertisements out that link. Okay, so typically on the provider edge, you would want to use both of these commands, because we want to make sure that we're not leaking our AutoRP advertisements out, and we want to make sure that we are not accepting auto RP advertisements. Okay, because we don't want people using our RP addresses, but we also don't want to use theirs. Okay, and the same with the BSR border. So we're going to do this on router 2 and router 4 and apply both of these configurations to the Ethernets. Okay, technically we only need to do the auto RP on router 2 and the BSR on router 4, but in a practical implementation, the service provider would do both of them. Okay, so first thing we're going to do is create an access list that is going to match and deny those auto RP groups. Okay, the auto RP groups again are 224.0.139 and 224.0.140. Now, if you don't remember these, you can look in the multicast routing table, and if we say show IP mroute, you can see that router 2 is sending to this address, and router 2 is sending to this address. Okay, since it is a mapping agent and a candidate RP, it is sending to both of them. Okay, there's a question here. What if the service provider is not running either auto RP or BSR? Okay, in that case, you really still want to configure the filtering. The reason why is that auto RP messages take precedence over statically configured RPs. So even if you have a static RP assignment, if you receive somebody else's auto RP message, you will switch over to use auto RP instead of the static RPs. Okay, there's another way that you can prevent this on the individual routers. We could say on router 1, for example, we could say IPPIM accept RP. Then we could say accept only advertisements through auto RP. Or we could say specifically this address. Okay, now it really depends on how much configuration and administration overhead this is going to be, because doing BSR and doing auto RP, the reason that you're doing this in the first place is that you don't want to go to every single device and have to do manual configuration. Okay, a more secure way would just be to go everywhere, configure the static RP assignments, then we could say no IPPIM accept RP auto RP. So that's going to say deny all auto RP advertisements. Okay, then at the network edge, to make sure no one's messages are coming in, we would go ahead and configure these the filters with the multicast boundary and the BSR border. Okay, so on router 2 here, we'll say access list 1 deny 224.0.139 and 224.0.140. Okay, we will permit anything else. Okay, we could say the specific multicast address range or just everything. It's only going to apply to multicast regardless. Okay, then at the interface level, we'll say IP multicast boundary 1 and IPPIM BSR border. So don't accept or send traffic to these groups out the interface, and do not accept or send BSR messages. Okay, so we can see at the interface level we have the IPPIM BSR border, the IP multicast boundary, and then we have our access list in global configuration. Okay, so we'll go ahead and drop the same configuration off on router 4. Okay, now if we configured PIM on the interfaces before doing this, we would have seen an error in where the join messages and where the register messages were being sent to. Okay, now at this point, router 2 and router 4, they're not exchanging unicast routing information about their loopback interfaces. So what would happen is that the devices inside AS456, they would be learning about an auto RP that they did not have a route to. So when they went to send their join messages, their PIM join messages, or their unicast register messages, those would have had unroutable entries, and those packets would have been dropped. Okay, so you need to make sure that your RP assignments are correct based on what your network design is going to be. We need to make sure inside AS456 they're choosing router 4, and in AS123 they're choosing router 2. Okay, but by configuring this at the network edge, we're ensuring that that is going to be the case. Okay, so now between these neighbors, between 2 and 4, we're going to run PIM, IP PIM sparse mode. IP PIM sparse mode. Okay, now even though we are running PIM between the neighbors in the inter-AS configuration, they're only going to have state information about the specific groups that are transiting their network. Okay, so if we have 10,000 sources that are inside AS123, only the MSDP peer inside 456 is going to have that state information. Okay, not everyone in the transit path is going to have it unless there are either sources that are trying to send to those destinations or there are receivers for those destinations. Okay, so if we look on router 4 now, and we show IP PIM neighbors, okay, we see we're adjacent with router 2. If we say show IP M route 224.78.78.78, we see not only do we have the star comma G entry, but now we have the specific source comma group entry. So we're saying that it's coming in the Ethernet, which is going towards router 2, and it's going out our serial interface down towards router 5. So if we go back to the source now, and we see that we're not getting replies here from router 8. What we're going to do now, step by step in the transit path, we're going to go ahead and debug the traffic to see exactly what's happening on a hop-by-hop basis. Okay, at this point, there really shouldn't be an error in our configuration. It's most likely related to convergence right now. Okay, so if we went around and cleared the multicast routing table, we should see that the traffic is moving end to end. Okay, but if we did run into a problem like this in the exam, what we can do is on a hop-by-hop basis look at what's the incoming interface, what is the outgoing interface, is there an RPF failure, and if there's not an RPF failure, is the traffic correctly being forwarded between the interfaces? Okay, so if we go to the first hop here, let's undebug, and on all of these interfaces, what we're going to say is no IP mroute cache. Okay, just like when we were doing our unicast debugs, we need to disable fast switching for multicast in order to get this to hit our debug output, because only process switch traffic can be debugged. Okay, so we'll say no IP mroute cache, we'll say logging console, and debug IP mpacket. Okay, so we can see here on router 3, we are receiving traffic in Ethernet 0/0, 10.1.37.7 is the source. It's going to 224.78.78.78. We are forwarding it, multicast forward. We're forwarding it out serial 1/2. Okay, that's the correct output we should see. Okay, so it's coming in from router 7, we're forwarding it out to router 1. We do the same thing on router 1. We'll say IP, no IP mroute cache on the serial and the ATM, and debug IP mpacket. Okay, so on router 1, we see it's coming in the serial from router 3, which is the correct source. It's going out the ATM, multicast forward. We're forwarding it. Okay, so that is the correct output we should see. If we look on router 2, we'll do the same thing. We'll log back to the console, logging con. On the ATM, no IP mroute cache, and on the fast Ethernet, and we'll debug IP multicast packets. Okay, so we see it's coming in the ATM link from router 1. It's going out fast Ethernet 0/0 towards router 4, multicast forward. Okay, so now we can see between the autonomous systems, we do have the multicast traffic flow. Okay, so let's take a look on router 4. Log back to the console. On the Ethernet, we'll say no IP mroute cache. And on the frame relay, then debug IP mpacket. Okay, so we are forwarding it. It's coming in from router 2. We're forwarding it out the serial over to router 5. So on the transit interfaces, no IP mroute cache. Ethernet 00 and 01. Bug IP mpacket. Okay, so we received it in the serial. We're sending it out Ethernet 0/1 over to router 6. Okay, so everything through router 5 is correct now. On the gigabit Ethernets, no IP mroute cache. Then debug IP mpacket. Okay, so we are forwarding it all the way out to the client. Okay, so something's going on with router 8 where it's not responding to the packet. Let's go back to router 7. And let's try this. Let's go ahead and try this with a new traffic flow. Okay, so on router 8, let's go ahead and join a new group. Okay, sometimes what you'll see, this IP IGMP join group command, it'll time out after a while, and the device will stop responding to packets that are being sent to it. Okay, you can refresh it by taking the command off the interface and then reapplying it. Okay, so we'll go to Fast Ethernet 6 here. We'll say IP IGMP join 224.87.87.87. Okay, so once this join is sent, we should be able to go to the rendezvous point for this network, say show IP mroute 224.87.87.87. Okay, we should see our star comma G entry, which we do. Okay, once router 7 starts sending into the network, we should have a unicast register occur to router 2. Router 2 will generate a source active message to router 4. Then router 4 is going to merge the source tree and the destination tree. Okay, so on router 7, we'll go ahead and ping 224.87.87.87. Sending commands yes. Sending it out Fast Ethernet 03. Source is 10.1.37.7. Okay, so if we look on router 2, show IP mroute 224.87.87.87. We have the S comma G entry. It says it's coming into ATM, we should forward it out to Fast Ethernet. If we look at router 4 and say show IP MSDP source active cache, we see we have that entry. Okay, so router 2 told us that the source 10.1.37.7 was sending to 224.87.87.87. If we look at the multicast routing table, we see that it's coming in the serial, or it's coming in the Ethernet. We're forwarding it out the serial. Okay, so router 4 did merge the star comma G tree with the S comma G tree. So now we should see that the packets are end-to-end. So if we debug on router 6 again, debug IP mpacket, And we can see that the traffic is coming in gigabit 00 and forwarding it out gigabit 01. Okay, now in this case, even though we're not receiving the echo replies back, it doesn't really matter because multicast traffic is always a unidirectional traffic flow. What we care about is, can the traffic get from the server to the client? If the client typically is not going to be sending traffic back to the server, it's not going to be sending unicast traffic back. Multicast is going to be the unidirectional traffic flow. So as long as from router 7, we can send the traffic into the network and it propagates end-to-end down to the final outgoing interface, then everything is working correctly. Okay, another way that we could test this without doing the IGMP join would be on the outgoing interface of router 6. We could say on gigabit 01, I want to add the group 224.666 as a static entry in the outgoing interface list of the multicast routing table. Okay, so when we say show IP M route 224.666, we're going to see gigabit 0/1 in the outgoing interface list. So statically, we're entering that in there. It means that we do not need an IGMP join or we do not need a PIM join in order to build that outgoing interface. So if we say show IP M route 224.666, we see statically we have the gigabit 01 in the outgoing interface list. If we look at router 4, we should see likewise a star comma G entry for this. It's not coming in from anybody, but it should be sent out the serial. If we go to router 7 and send traffic to this destination, 224.666, going out fast Ethernet 03 from 10.137.7. And if we look at router 6, we can look at the show IP M route count output, and it's going to show us what sources are sending to what destinations in the network. Okay, so we can see there is a entry for 224.666. 10.1.37.7 is sending it to there. And we can see that we are forwarding packets. We received 7 packets so far. We forwarded 7 packets out the gigabit interface. Okay, we don't see the outgoing interface here, but if we looked in the multicast routing table, we would see that. Okay, what this will also show you is RPF failure occurring on the group. If we see in the other counts here, we would see RPF failure over here. Okay, so if we see this number incrementing here, that means that we're dropping packets due to an RPF failure. Okay, there's a question here. After we're done troubleshooting, should you put multicast route cache back on the interface? If this was a real implementation, then yes. But in the lab exam, it doesn't really matter. If you see some quirky behavior with it, you may want to go ahead and put it back on. Like we saw in quality of service, we had some issues with where turning route cache off was causing some problems with that. So after you're done troubleshooting, you may want to put it back on and test your reachability. Now, what we could have done here, we didn't necessarily need to look at every step-by-step hop in the transit path. We could have looked at just router 6 and see it and look at the count to see if it was sending it out the interface. But when you have an RPF failure where you see that the traffic is not getting transited through, you need to look at it on a hop-by-hop basis, starting at the source, going away from the source towards the destination. Okay, so any questions so far on the multicast source distribution protocol example we had? Okay, the next thing we're going to take a look at here is multicast BGP. And now typically what you will find on the internet is that the multicast peering arrangements and the unicast peering arrangements are typically not going to be the same path end to end throughout the internet. And now the problem with running multicast on the internet, unless you are tunneling it inside something like GRE, every hop in the transit path is going to have to be running multicast. Okay, so that means that basically we're running PIM sparse mode end to end over the whole internet, and that all the autonomous systems are exchanging MSDP information to advertise sources and destinations. Okay, what multicast BGP is used to do is just for the purpose of performing an RPF check. A multicast BGP does not have anything to do with advertising multicast sources, nor does it have anything to do with advertising the clients that are trying to join. Okay, so multicast BGP does not integrate with PIM in order to communicate about who is sending or who is receiving. We still need to run PIM end-to-end on every interface in order to get multicast transit. Okay, but what multicast BGP is going to allow us to do is have a different transit path for our unicast versus our multicast. Okay, so the problem that we're trying to solve, we have a unicast route to the source S that is sending multicast traffic. When we look at the unicast route to the source, we see it's reachable via AS1. But we're not running multicast routing with AS1. We're running multicast routing with AS2. So the problem we run into is that when we receive a packet from that source, and we do a lookup on the unicast route to perform our reverse path forwarding check, we're going to drop the traffic if the incoming interface for multicast is not the same as the outgoing interface for unicast. A multicast BGP is going to allow us to get around this problem by choosing selectively where we want the multicast information to be advertised. Okay, so what we're going to do here is we're going to bring up another link between router 1 and 5, and we're going to run a unicast BGP on the link. Okay, we're going to keep our multicast domain set up as it is now. So between router 2 and router 4, we're running MSDP, and we are running PIM. Okay, so PIM and MSDP between 2 and 4, and we're also running unicast BGP. Okay, with unicast BGP, we're advertising router 7's link, and we're advertising router 8's link. Okay, there's a question here. Can we save the configs for MSDP? I'll save the config after we're done with the multicast BGP. There are examples for this in the Tech Lab series for Anycast, for MSDP, and multicast BGP, and the examples are pretty similar. So I would recommend after we're done with class, you definitely want to make sure to go through that stuff and do the configuration and do the verification on a hop-by-hop basis like we were. Okay, so what we're going to change here for multicast BGP, we're going to run BGP between router 1 and 5, but we're not going to run PIM on that link. Okay, so we're only exchanging multicast between router 2 and router 4. We're not going to exchange multicast between router 1 and 5. Okay, so let's go ahead and take a look at the command line here. Okay, so on router 5, we'll go ahead and bring this interface up. No, shut. And under OSPF, we want to make sure that we're not exchanging IGP information with router 1. Okay, so we're not running IGP between the different BGP autonomous systems. We're running just unicast BGP. So I'll say passive Ethernet 0, 0 here. Okay, because we want to prevent this OSPF adjacency, basically. Okay, then under the BGP process, we're going to peer with router 1. Okay, same thing on router 1. We should have connectivity to router 5 now. And under OSPF, we'll say passive fast Ethernet 1, 0. And under BGP, router BGP 123, we're going to peer with router 5 with regular unicast information. So from router 7, we should still have unicast reachability over to router 8. And let's go ahead and trace to that destination, trace 10.168.8. It says we're sending the traffic to 3, 3 is sending it to 1, 1 is sending it to 5, 5 is sending it to 6, and finally 6 sends it up to 8. Okay, the previous path that we had, it was going from 3 to 1 to 2, then 2 was sending it over to AS456, over to router 4, then it was going up from 4 to 5 to 6, then finally on to 8. If we look at the BGP table now in AS456, if we go to router 5 and say show IP BGP 10.170, 10.137.0. Okay, we have two different paths to the destination. Okay, we have a path from router 1, and we have a path from our route reflector client, who is router 4. Okay, so we have two different paths. We need to run the BGP best path selection process. Okay, first thing we look at is the local preference. We see that local preference is 100 on both of these routes. Okay, actually, before local preference, we look at the weight. Okay, we're not manually configuring the weight here on router 5, so we see that there is no weight value set. Okay, so we look at the weight. There is no weight. We look at the local preference. Both of them are 100. Then we look at the AS path. We can see the AS path is 123 out both of these. We look at the origin code. Origin code is IGP for both of them. And we look at the metric value, the med. Okay, there's no med. Actually, let me bring up the. Let's bring up the documentation page real quick on this. Okay, you definitely want to know what the BGP best path selection is. You don't necessarily need to memorize it though, because you can look it up on the documentation CD. Let me share out my web browser here. Okay, so from the main documentation page, we'll go down to iOS. We'll say iOS 12.2, configuration guides and command references. We're going to go down to IP configuration and routing protocols and configuring BGP. Okay, so in this document, first thing we're going to look at says how BGP selects paths. Okay, so it's saying, first off, if we don't have a route to the next hop, do not consider it. Okay, if we do have a route to the next hop, and the synchronization rule is, or the synchronization is enabled, then we have to have an IGP route to the destination. Okay, like I mentioned previously, synchronization is effectively deprecated. It should be disabled always whenever you're running BGP. Okay, so then we go through the BGP attributes. We look at the weight. We saw that was the same. We look at the local preference. Both of those were the same. Neither of these are locally originated by the router. Then we look at the AS path, shortest autonomous system path. We saw both of those were learned directly from AS123, so it only had an AS path of 1, or length of 1. Okay, then we have the origin code. We see both of those were IGP because they were originated by the network statement. We look at the med value. Okay, the med was null in both cases. Then it says we're going to prefer eBGP over iBGP. Okay, so from router 5's perspective, this is where the decision is happening in the BGP best path selection. Router 5 is going to choose to route to router 1 instead of routing to router 4. Because typically what you'll see, if you are learning a prefix from BGP, it means that it is outside of your autonomous system. Your own internal information, you should be routing it via IGP. You should only be routing BGP information that is outside of your autonomous system, or at least related to unicast. For things like MPLS, we will be using multi-protocol BGP to route within our own autonomous system. Okay, but for IP version 4 unicast, typically you're going to see that you should be routing IGP over BGP for your internal information. Okay, so we want to prefer eBGP over iBGP. That's what we see is happening here. Okay, so when router 5 is choosing its best path, it's saying, I'm going to get to this via router 1. Now, what this is going to cause to happen, if we look back at the command line here, if we show IP PIM neighbors on router 5, we see that we're adjacent with router 4 and we're adjacent with router 6. We're not adjacent with router 1. We're not running PIM on that link. Okay, so if we go to router 7, and we're going to ping, we'll ping 224.6.6.6. We saw previously the end-to-end transit path was correct for this. Okay, we saw that when router 7 was sending traffic to this, router 6 was receiving it and forwarding it out its LAN interface. Okay, so we'll set a high repeat count. Extended commands, yes. Interface is going to be out fast Ethernet 03. Source is 10.1.37.7. Okay, so if we look at router 2, show IP mroute count, we see that we are receiving traffic from 10.1.37.7, and we are forwarding it. Okay, if we look at this again, we should see this incrementing. And we see that we are receiving the packets and we're forwarding them. We're forwarding them out to router 4. On router 4, if we say show IP mroute count, we see we are receiving traffic from that source to 224.666. We are forwarding it. If we go to router 5 here, show IP mroute count, we're going to see that as we are receiving this traffic, this packet's forwarded 28. Let's take a look at the routing table of router 5. Show IP route. It says 10.1.37.0 is reachable via router 1. Router 1 is reachable out Ethernet 0/0. Okay, let's debug IPM packets on router 5. Okay, we see router 5 says the RPF neighbor is 150.1.15.1. If we do our unicast lookup on this, show IP route 151.15.1, says it's reachable via Ethernet 0/0. Router 5 actually should be dropping this traffic, but it's not. Let me clear the multicast routing table. Let's try this with a new group on router 7. Okay, what we should be seeing here is that router 5 has an RPF failure and it's dropping it, because what's happening, the multicast traffic is coming in serial 0/0, but the unicast route is pointing out Ethernet 0/0. Okay, so let me clear the multicast routing table everywhere. Their IPM routes. And let's try this with a new group on router 8. Okay, let's say at Fast Ethernet 6, we will join IP IGMP join 224.123. Okay, then from router 7, we'll go ahead and send traffic to that destination. We'll ping 224.123. Any commands? Yes. Going out, fast Ethernet 0/3. Source is 10.1.37.7. Okay, we see that router 5 is receiving the traffic. It should be dropping it, though, instead of forwarding it. So for some reason, router 5 is not performing an RPF check on that traffic. Okay, let's go ahead and take a break. Let's start back in about 10 minutes, and then we'll continue to verify this.